Давайте поступим следующим образом. Я представлю Наташу Шарыгину из университета Лугана, а Наташа представит всех остальных, что. Вот, то есть немножко по-другому будет пойдем. Пожалуйста.
Здравствуйте, очень приятно вас видеть. Мы приехали к вам в университет Лугана, и я представлю своих коллег. Я сама из России. Я могу говорить по-русски, но то есть, если у вас будут какие-то проблемы с английским, вы можете меня попросить и помочь понять лучше. Но вообще-то наши занятия будут все на английском. Включая меня, я только буду читать текст на английском. Okay, so now I'm switching to English, so my colleagues can understand me. So essentially, I would like to introduce you to Professor Fernando Pedone and Fernando Pedone. So we are starting a series of lectures, which will take 2 weekends, this weekend and the next one. Do you understand me, by the way?
Yes.
Yes. Okay, good. Who doesn't? I mean, it's not a good question. Who understands me?
Who doesn't know?
Please raise your hand. Okay, so again, majority at least. Good. So we will start from just a brief introduction to our university and to our department, and we will just tell you the purpose of our visit, and then we will go into the particular subjects. So today you have 2 lectures, one on distributed computing and on networking. So Antonio and Fernando are going to teach. Okay, so essentially, as I said, we are called the University of Lugano. In Italian it sounds like Università della Svizzera Italiana. And we are members of the computer science department. And we are 3 professors from this department. So this is a small map of Switzerland, for those who don't know where Switzerland is. So it's a small red dot right in the middle of Europe. So it's the heart of Europe, it's the heart of everything, really, the core country. So, and in Switzerland, we are located in the most southern part, right next to the border with Italy. So people in the Italian part of Switzerland speak mostly Italian, so they quite fluent in English. So, in fact, our university is teaching. Our department teaches only in English. So, however, a lot of people speak Italian. For example, Antonio is Italian himself. So, and he will introduce himself later, tell you about his background. So, right. So, Lugano is the most beautiful city in the world. Without any exaggeration, by the way, it's really beautiful. It's Mediterranean climate. It's very warm, so it's right on the lake. It has a lot of palm trees, and it's surrounded by the Alps. So we have snow and sunny weather at the same time, most of the time. So it's here. And so this is the picture. Can you see it well? The city, it's a relatively small city compared to St. Petersburg, which is really nothing. It's only officially how many people?
Maybe 60,000.
60,000 people. So Switzerland is actually a relatively big city. So the biggest city in Switzerland is Zurich, and it's about 500,000, I think, so more or less. So it's small compared to St. Petersburg, which is so huge, for example. So all Switzerland is about 6 million people, just like St. Petersburg. So, well, okay, so this is essentially the picture. So the city is right on the lake, so surrounded by the mountains, and some time ago, in fact about 14 years ago, the Swiss government decided that this area needs a university, and they decided to establish a new university. And it's essentially a start-up when a lot of funding is being invested into just establish a strong university in the Italian part of Switzerland. So it's the youngest Swiss university as a result of this initiative. And there are 4 departments right now: economics, computer science, communications, and architecture. So altogether, it's about 150 professors and teaching associates. about 100 PhD students and about 1,600 undergraduate students. So the students and the teaching people come from all over the world. So in fact, it's as you can see, for example, for the professors, the Swiss representing minority, only 40%. And in our department, we have only 2 Swiss people. So Fernando is one of them.
Man, not really.
Which he will explain you maybe later that it's not exactly counts. So but officially he is Swiss. And as far as the students are concerned, so also we have a mixture of students from all over the world, mostly Europeans, different countries in Europe, including Russians. So we also have some Russian students. So here's, by the way, the main building of our university on the top, white. So this is our department, this is our building, it's where we all have offices. It's brand new, it's only 1 year old, we moved last year. So the focus of our department is on research. Our core priority is to make sure all of us do strong research, that we publish, that we are competitive in the world market. So we have very strong people. So everyone is very competitive and has an excellent reputation in terms of research. So there are several areas. However, the focus of the department, because it's relatively small, is on computer systems. So we cannot be completely diversified as a huge university would be, but so we decided to keep strong and stay strong, to focus on theory and systems research. So here's the list of some areas, and those are software engineering, distributed systems, automated verification, and networking. And in fact, in this series we are going to teach here, we will be representing all of these topics. So the purpose is just to give you an introduction to what these areas are about, and if you're interested in more advanced studies and more focused research, we would be happy to consider you to become our students. And the idea is that you take our classes, so you will have lectures, and then at the end of the second session you will have an exam on May 3rd. And we will tell you later how we will do it. The exam will be in English, so it will contain written and oral part. So we will speak to each of you and see how interested you are, essentially. It would not be too difficult for you because the courses are rather short. We won't be able to go into too many details. So it will be easy to study and prepare. But we want to see, your motivation. We want to see if you could demonstrate that you potentially in the future could become a good student and be interested in research. So we will be offering 2 types of scholarships. One is to do master's studies. Master's studies is something goes after the bachelor's degree. So you're supposed to already have finished your bachelor's studies, which is 3 years of the university, right? 3. So, and master's studies are 2 years. So, and you take classes, you do master's project, and you become a master in computer science. It's one option, and the other option is to do PhD studies, which corresponds to aspirantura in Russia. So, and PhD studies are longer and much more focused and much more dense, like 4 or 5 years. And we will give you an option also to become a PhD student with us. But it will be rather competitive, so we will be making offers to the top people who do well during the classes and at the exam. Yes. So I guess, would you like to add something?
Well, we need just one thing. We brought some materials, some flyers, and more information about the university and the courses. So if you guys want to learn more about the University of Lugano or the fact of informatics, can get some flyers here after the presentations.
Do you like to add something?
No, I guess we can then introduce ourselves later.
So then let's take like 2 minutes we would like you to answer on these questions. Just
Starting
take
now.
a piece of paper and very briefly and quickly answer this question. So we will take all the issue and contact. Them our email address. Right? My the first lecture is Fernando Pedone, distributed algorithms. See you later.
Okay, guys. So I'd like to start by saying, by thanking you all for coming here on Saturday evening. So I really appreciate it. And I'd like also to say that I'm very happy to be here and share a little bit with you my area of research, which is distributed algorithms. It's my first time in Russia, and so I arrived yesterday. Didn't have much time to walk around, but I did some walking today, and I found it really nice. It's a very beautiful city, very beautiful building. So I'm really happy to be here. So my main area of research is, broadly speaking, is distributed systems. So in the area of distributed systems, I work on theoretical aspects of this field, which is called distributed algorithms many times. And I also do some research on more systems aspects, which basically mean implementing things and measuring their performance. I'm not going to spend much time talking about that. Tomorrow I intend to spend some minutes at the end of my lectures telling a little bit more about this other component of my research. Right? So most of the time it's going to be about distributed algorithms. And what I have planned for this weekend, basically I'll be teaching only today and tomorrow. I will be coming here next week. Is basically summarized here, right? And by the way, how many of you have been exposed to distributed algorithms? Okay, there are a few hands up, more or less. So maybe this topic is familiar to some of you, even if you have studied this, I hope to give you at least a different perspective on the field. Right? And if you have any comments during my presentation, don't hesitate to raise your hand and ask me. Right? I think it gets much more interesting if this becomes a conversation more than just me presenting and speaking all the time. So I will start by telling a little bit about the way we model distributed systems, and which basically represents how we reason about distributed systems. And so I'm going to tell a little bit about different models, how you see complex systems. Real systems are very complicated. Since here in distributed algorithms we are more interested in theoretical aspects of these systems, we have to remove many of the details that are not actually don't matter, and that's what I mean by models, right? And then I'm going to tell you maybe today and continue tomorrow about one of the most fundamental problems in distributed computing from a theoretical perspective, which is the consensus problem. So in many distributed systems, the actual problem that's being solved is called consensus. And it turns out that this problem has been studied for many years. There are many different ways of solving it. And so we're going to go through some of this. First, define the problem, and then see some implementations of this problem. And then we're going to tell you about fault-tolerant broadcasts. It's a related problem. And I'm going to start by defining the problem formally, and then showing you, if I have time, some algorithms on how to implement this in different systems. And finally, but although I don't think I really will have time to do this, I may tell you a little bit about atomic commitment, which is also a known problem, mainly if you have studied databases. Okay? So that's for the introduction. So are there any questions so far?
This is content for today or for 2 days?
It's for 2 days, yes. Oh, actually, basically I took these slides from a course that I give at the master's and PhD levels, and I'm going to go as far as I can. So, distributed system models. Let me start by showing this. So the first thing, this is all about intuition, right? And if you're going to build a system, you're going to design an algorithm, you're going to have some intuition about how you're going to build this. And of course, you can formalize your intuition somehow. But just because you have a formal model, it doesn't mean that you have a solution to the problem. So, and I'm going to show you that it takes more than just Chinese astrology to actually solve a problem. So what I mean by developing an intuition? So there are basically two broad approaches to solving a problem. One is based on experimental observation. So you build a system and then you observe its behavior. Right? You have to solve a problem. For example, you have to build a database. Right? And see how you have to implement some relationship between data. You have to analyze the data and correlate it. So one way would be to build a database and use it to do this, to solve this particular problem. So you build the system and then you observe its behavior. And another approach would be to take the problem, simplify it, removing unnecessary details or aspects of the problem that you find are unnecessary, and then basically you simplify the problem and then you analyze this problem. And so these are two complementary approaches. Some people tend to concentrate more on one, other people tend to concentrate more on the other. And basically what I'm going to do now is to concentrate on the second, so how to model and analyze a system. So before actually telling you anything about the model, we have to agree about what's a model, right?
And before that, we should agree what is the system, right?
Right, yeah, so I could go on and on here, but at some point, so that you can actually go ahead here, the definition of a system is not really that important right now. Let's tell a little bit about what a model is. So it's basically some attributes, some characteristics, or a set of rules that are going to determine how we can reason about our system, right? And can a model be wrong? Well, that's a difficult question to answer, right? It's really relative. So I actually, on thinking about this question, I like to take the perspective of Manfred Eigen, who says that a theory has only the alternative of being right or wrong, right? But a model has a third possibility. It might be right but completely irrelevant if you abstract too many details about your system, right? I think it's going to become a little bit more clear as I show you some examples. So basically, so what's a good model? You can have accurate models. So this means that you can get, they model very well the particular system that you are reasoning about. And then you can have tractable models, which basically means how easy it is to solve the problem in this particular model. And it turns out that you can have everything, right? In general, if you have a very accurate model, which really is very rich, allows you to make lots of observations about your system, it turns out that it's very hard to analyze your system. And you can have the very extreme where your model is basically a particular system where you want to solve the problem, full of details, and it turns out that it's very hard to actually solve the problem in this model. On the other hand, you don't want to oversimplify, because if you oversimplify, it means that the results you have found are going to have little use in reality, right? Because basically your model is too simple with respect to what you actually want to do in reality. So it's like a game, right? You have to find the right level of detail to model your system so that you can say interesting and useful things about it, and but don't want to have too much detail. So what kind of things can we expect from the model? What kind of answers can we extract from the model? So one of them is feasibility. So is the particular problem you are interested in solved in this model? Or you don't even have to try to find an algorithm. You can show that there is no possible algorithm that's going to be that can be designed for a particular problem in this particular model. So another perspective is the cost of a given algorithm in a given model. So assuming that the problem can be solved in this model. Right? So let me show, so far it has been quite abstract. Let me show a more detailed example. Let's talk about the coordination problem. So I have here two processes. So processes is already, we talked about the model, is the entity that can perform operations, right? Like a computer is being modeled here as a process. It can perform some computation. And we have two of this. We have processes A and process B. And they can communicate by exchanging messages. So notice here, using a bidirectional channel. I'm not talking anything about what kind of protocol I'm using. So for those who have some notion of networks, I'm not interested in what kind of protocol they're using, whether it's TCP or UDP. I'm just saying that there is a link, and there's two processes which can be. They can be computers, they can be processors, they can be whatever you feel like. They can be a person. And they're communicating. And they use this particular communication link to exchange messages, right? And I'm saying that neither process can fail. So they will always be operational. They can always perform some computation. But the link may lose some messages. So one process can send a message to the other process and the message doesn't arrive. And the process can't know whether a message is going to arrive or not. And they can execute two operations, which here I'm saying alpha and beta. It doesn't really matter what these operations are. But there can be two different operations. So what you have to do is to devise a protocol in which both processes, they take the same action. So let me tell you a little bit more. They start with an initial state which reflects the action they want to perform, alpha or beta. So they can use this link to communicate and exchanging messages. And at the end of the computation, they have to agree whether they're going to do alpha or beta, despite the initial state in which they started. So is the problem clear? So how would you solve this?
What kind of information they can pass to each other?
Whatever they want to send. They can send messages. These messages can contain whatever they feel like.
And what is what kind of losing of messages can be in the channel? What do you mean by a channel may lose messages?
So one process sends a message to the other process, and the message never arrives, and you never arrive because the message was lost. And then it can happen that the process sends another message, and then this second message gets through.
For example, all messages are lost; they will never.
Sure. Yes. So yes, if all messages are always lost, so the problem is unsolvable. It's pretty easy to realize. Now let's make things a little bit more interesting. Not all messages are lost for sure, right? You don't know. You hope that by resending messages, eventually they're going to get there.
Does the sender know that the message is lost?
No, it doesn't know. Yes, it doesn't know. Right? Which is usually what happens. You send a message through the wire, you hope that the message gets through it, but you don't know whether it does or not.
Is there any high probability that the message gets through the channel?
No, I'm not assigning any probabilities to the channels.
Is it positive? Or is it negative?
There is a probability that's bigger than zero that the message is going to be lost.
Why does not TCP protocol fits?
Well, because TCP, when you get after you have TCP, you assume that there is reliability, right? So messages are not going to get lost.
I mean, they can lost. I don't know.
Well, in principle, what TCP gives you is reliable message communication, right? So and then it's built on top of something else. So I'm considering the lowest level. Well, I don't want to spend too much time on this. I'm just going to give you a flavor of what defining a model is. Yes.
Okay, I mean, why doesn't the protocol one have a default action alpha, and if I send a message and receive an answer on my message, we execute beta? Why doesn't?
Yeah. So I think I have to give more information about this. So if both start with alpha, I want alpha to be the final action, and if they both start with beta, I want beta to be the final action. Well, it turns out that as defined, right, as stated, this problem it cannot be solved. And let me give just a brief intuition why in this particular model that I just defined, right? If you assume, for example, that the communication is reliable, or if I make different assumptions, I know how many messages could be lost, then it's a different story. But as defined, there is no solution. And in fact, it's not very hard to understand why. So here's a very simple proof by contradiction. So let's assume that any protocol executes in rounds of message exchange, right? I'm generalizing a little bit how the protocol is going to work, but it's not a big generalization. So first, let's say that process A sends a message to process B, right? Then B sends a message to A, and so on. So that's the way they work, right? A sends a message to B, B sends a message to A, and I'm saying that A starts. Doesn't really matter. And if you want, this can be easily cover the case where one process sends more than one message, right? You could group them all in a single one. So assume that P is this protocol that solves the problem, right? And P is an optimal protocol. Optimal in the number of runs, so in the number of messages that it sends. So P sends the fewest, solves the problem in the fewest number of runs. So one message to one side, another message to the other side.
What if we don't know the number of rounds of P? What if we...
No, it doesn't matter. Right. No, it doesn't matter. I'm saying that P is optimal. I don't know the number of rounds. I'm just saying it's optimal. So it's the best protocol. It's an assumption.
Maybe there is no optimal protocol.
Oh, that's exactly what I'm going to show, right? That's why it's a proof by contradiction. Assume that it exists. So I'm going to show you a contradiction which basically proves that there is no such protocol. So if there is a protocol, and this protocol that's how the proof is built, right? Let's assume that the protocol exists. And now let me show an argument that is going to lead to a contradiction, which basically, from which you can conclude that the protocol doesn't exist. So assume that P solves the problem, and more than that, it's an optimal protocol. So it solves using the fewest number of rounds. And assume that the last message is sent by A, and let's say that this message is M, okay? So here are two observations. The first one is the action taken by A can't depend on M, right? The value that A is going to decide, alpha or beta, can't depend on M. Why? Because A knows that this message can be lost. It doesn't know whether the message was lost or not, but it can be lost. So it cannot depend on the last message to take an action. The second observation is that the action taken by B can't depend on M either, because M may also it should make a choice, even though the message is lost. So B knows that the message can be lost. So it turns out that neither for A nor for B the last message N matters. So if that's the case, we can revisit our protocol and remove M from it. But then it contradicts the fact that P is an optimal protocol that sends the fewest number of messages. Okay. So this result has been known for several years. I'm going to talk a little bit more about that once I finish with models. Right. So what have we learned about this example? So our protocols between two processes in this model are equivalent to a series of message exchanges. Right? That's not a big deal. I think more important than that, we have learned that this particular problem cannot be solved in this model. And actions taken by a process depend only on the sequence of messages that this process has received. Okay. So what else can we do? I guess you guys have helped me already. We can, from here, what we could do is, so let's reconsider our assumptions and see whether we can make the problem solvable all of a sudden. For example, what if channels never fail? What if the channel is reliable? Then it becomes a simple problem, right? So what if channels, they lose a bounded number of messages? Can we solve the problem? Maybe it's a bounded number, but maybe you don't know the bound. Can you write a protocol that will solve this problem in that case? What if processes know how many messages are going to be lost? Right. Or what if we try to generalize this problem for more than two processes? So basically that's how you can derive new problems, right? And new results by revisiting a known result. So what I'm going to do next is I'm going to give you some details about the models that I will use in the rest of my lectures. So the first thing to characterize is the synchronism or lack of synchronism of a system. So you can actually characterize systems in general by this characteristic, and I'm going to call an asynchronous system a system where no assumption basically is made about the execution time of processes, and by the time it takes for messages to be sent through the links, right? So it's a very weak assumption, because basically I'm not making any assumption at all. I'm not saying anything about how long it takes for a process to execute. So I don't know how much time it takes for a process to execute a step, and I don't know how long it takes for a message to be sent through the wire. So basically any system, most systems that are based on message passing, they satisfy this assumption. So it's, the nice thing about the asynchronous system that it covers many systems. So if you, for example, if you have to solve a particular problem and in a particular environment, and you want to make sure that your assumptions are going to be satisfied by this real environment, you can say, oh, let's assume that the system is asynchronous. So on the other end of this spectrum, you have synchronous systems, which basically you know what's the relative speed between different processes, and you may know exactly the time it takes for each process to execute a number of steps, and you also know how long it takes for methods to be propagated to the wire. Okay, so you know what's the longest. And it turns out that the difference between having this information and not getting information makes a big difference in terms of solving problems, as is going to be clear in a few slides. So how to choose? We have learned that there are two different sorts of systems, synchronous versus asynchronous. So how do you choose? I told you a little bit already. Since any system is asynchronous, a protocol designed for such a system will work in any other system. Do you agree with that? So my real system, just are that it's not going to violate my assumptions. So my model characterizes my real system accurately. So it means that if I write a protocol, an abstract protocol for my asynchronous system, it's going to work in the real system. So why not writing protocols for the asynchronous system only? In which sense?
For example, in pass-through in count of messages we should send between.
More or less. Well, it turns out that the reason why we don't simply write our protocols for asynchronous systems is that because many problems that cannot be solved in asynchronous systems. So I just showed an example. The coordination problem is an example. In the system as described, it can't be solved. So does it mean that computer systems cannot agree on a value? Well, it means that we have to strengthen a little bit our model, right, with some further assumptions than simply using a completely asynchronous systems. Well,
I'm sorry.
Yes.
Is the problem theoretically solvable if we do not have any bounds for message delivery time or for action execution time, but we have a synchronous time?
Yeah. So there are many things in between these two systems that I presented, right? I'm telling you about the synchronous in one end and asynchronous on the other. But in reality, there are many things in between. So we can make assumptions, for example. We can make something along the lines of what we're saying. We can do things like eventually synchronous systems. It means that for a certain time there is no synchrony in the system, but eventually there's going to be some synchrony in the system. So all these different flavors have been studied, and there are many ways you can characterize the system. Yes, there are different ways you can do that. Let me turn the question now. Let's say, we just saw why we cannot simply use the asynchronous system to model every existing system, is because many problems are unfortunately unsolvable. Now, why not model the real systems as synchronous then? Well, it turns out that many real systems, they are not synchronous. So you can build a real system that is going to be synchronous, but this is a very specific one. Let me give an example. The internet. The internet is not synchronous, right? You send a message, you don't really know how long it's going to take to the message just the other side, because many things happen in the way. So if you want to make sure that your problem is going to work in practice, you better not model the internet as a synchronous systems.
The internet, synchronism is the time.
Yes.
It's different on different faults, but pretty the same. So depending on different protocols, it may differ in 1 day or it may differ in 1 second, but still.
Yes, but that's what I mean, right? It doesn't behave as a synchronous system. There are some differences between, you can send 2 messages, one after the other, and these messages are going to take different times. So what can you do? Of course, what you can do is say, oh, let's be very conservative and assume that this delay is very large, right? And then let's design systems, and then let's assume that the internet, for something similar, is a synchronous system. But then there's a price, because you are being very conservative, and then in the end your protocols are going to be inefficient, right? But in reality, if you can model the internet or a similar system as with something that is weaker than synchronous, you can have more efficient protocols.
Do exist protocols which change a synchronous system and make it to be synchronous? So
that's I think that's a good point, because it reveals maybe some misunderstanding. So I cannot make my system synchronous or asynchronous. I can make assumptions about how the system works. Of course, I could try to build it, a real system, so that it behaves as asynchronous. But what I'm saying is, this is very expensive, basically, because you have to make sure that everything, there's no non-determinism in your system, so that whenever you send a message, this message is going to arrive in the right time. In reality, systems are all like that. I'm taking the perspective of the message, but you can also take the perspective of the local operation on the processes. So if you assume that every local operation, you know how long it's going to take, right? It has some practical implications, like what happens if you have several threads using the same processor, for example? Maybe your assumption about the time it takes to execute a step is going to be violated because the thread doesn't have the CPU, for example. So what I'm saying is it's dangerous to model systems as synchronous. Okay. So here's to illustrate the difference between modeling the system as synchronous or asynchronous. Let's look at another problem, another abstract problem, which is called the election problem. So here we have a set of processes, not only two, P1, P2, Pn, and this process they must select a leader. And the leader must be one process among these. And in each process, Pi has a unique identifier, okay, which is not known by the other processes. So what I have to do is divide an asynchronous and a synchronous protocol so that processes, they learn the identifier of the leader. They're going to exchange messages. We are still in the message passing system, so first they can exchange messages. And they're going to do that so that they can come up with the same leader at the end of that computation. So they can communicate by using broadcast, right? And let's assume that you don't have failures. So here's a protocol that solves this problem in a So is the problem clear? They have to agree on some identification of a process, which is going to be the leader, right? In the beginning of the computation, there is no leader. They're going to exchange messages, and at the end, there's going to be one process that's elected by the others. So an asynchronous system will be the following. So each process Pi broadcasts. So, and I'm assuming, notice that the communication here is a little bit different. So in this particular model, I'm considering they can use broadcast. So broadcast basically means send a message that everybody else is going to receive. Okay. So here's a protocol that solves this problem, right? This election using in an asynchronous model. So where I don't make any assumption about the time. So each process Pi broadcasts its information, so its UID, so the process identification, and waits for the receipt of every broadcast message. Okay. So what Pi does then, each process Pi does, besides sending this message and waiting for all, it collects all the responses and elects the process with the smallest UID. So do you agree that this protocol works? So messages can be lost, right? Processes do not fail. If you want to agree on some UID, you simply broadcast the message and then you're going to receive it. So this protocol here, it requires as many broadcasts as the number of processes in your system. Right? So here is a synchronous system. So let's see how we can actually solve this problem. So let's assume that there is some constant that is bigger than the largest message delivery delay. Okay, so that's how I'm modeling my synchronous system here. I'm saying there is some constant, and all messages, they are going to be delivered within this time frame. So tau gives me the time to communicate between two processes. And let's simplify a little bit the thing a little bit and assume that the local execution of processes takes no time, right? It takes 0 time to execute. So here's an algorithm that is more efficient than the other. Each process Pi, it waits for one of two events. Either it receives a broadcast message from another process, then it finishes, or then it waits some time. And this time it's going to wait is proportional to the time it takes for a message to go through the wire and reach the other processes, which we just assumed to be tau, multiplied by the UID of the process. Okay, so I forgot to say, each process has a different UID, right? It's UID stands for unique identifier, so they have different identifiers. So you wait some time, instead of, like in the asynchronous system, instead of simply sending the broadcast, you wait some time. You don't do the broadcast immediately. And this time is proportional to the time it takes for a message to be propagated, multiplied by the UID of the process. So As a result of this, right, what's going to happen is that processes, they are going to do their broadcast at different times. Right? They're not going to do it all at the same time. So how do we elect the process? The first broadcast is going to elect a process. Because the process with the smallest UID is going to be the first process to do the broadcast. So since tau is the time for the message to travel the wire, no other process is going to broadcast anything during this time. So with a single broadcast, I can solve the problem.
Well, but here you make an assumption that UID is small enough, so you could afford.
Right, that's a good point. It really depends what I'm optimizing for. And I'm optimizing here for the number of communication steps.
Why do we need those UIDs at all? Isn't I the unique identifier?
Yeah, I could say that. Yeah.
Do you work on the assumption that broadcast message is delivered to everybody?
Yes. No. Here, as I said before, the broadcast is delivered by everybody. It's not lost. What I'm trying to show here is the difference. Again, so we are optimizing for the number of messages that are broadcast, right? Is what you can actually gain from one assumption or the other. So if your system is asynchronous, it's hard to do better than what I showed you. So if you have a synchronous system, you can optimize your implementation. Okay. So let's do something else. Let's assign faulty behavior to the components of your system. So you have processes and you have communication channels, and you're going to say that some of these processes they can fail. And let me define more precisely what I mean by failure. So you can have some faulty components, and notice that differently from an approach where you try to quantify the faulty behavior by saying that the process is going to crash, I don't know how many times during a time interval. Here what you are doing is you are counting the number of faulty components. Right? So we're going to say that a system is T fault tolerant if it can tolerate up to T failures of these components. I'm not measuring. Another way of doing this is by measuring the mean time between failures, for example, and then say that the system is behaving correctly a certain percentage of the time. So that's not the approach I'm taking here. I'm counting the number of faulty components in the system. So here are some examples of how to model failures in a distributed system. So one kind of failure, one kind of way of modeling these failures is by assuming that processes are fail stop. This means that the process fails by halting, so it stops its operation. And once it halts, the process remains in that state, so it never recovers. And other processes, they can detect that the process has failed. Right? A weaker assumption is by saying that process can fail by crashing. The difference is that the process they stop the computation as well, and once they stop, they remain in that state. But a failure cannot be detected by other processes. So another process may not know whether a particular process has crashed or not. And this makes a big difference as well in terms of the algorithms. So if you want to be extremely weak in assumptions, so covering any kind of failure, or most failures that are possible in reality, you can assume that your process can behave in a Byzantine way or a malicious way. So this means basically that besides stopping the computation, they can do something to actually harm your protocol. Like in the previous examples that I gave you, the process will lie about their UID, for example. So a process has a particular UID, and you tell the other that it has a different UID, just to screw up the computation. So it turns out that these protocols, none of these protocols that I presented to you would work if processes were Byzantine. But it turns out that you can design protocols that work despite the fact that some processes are Byzantine. But of course, these protocols are much more expensive than protocols that make more strict assumptions like failure stop. So other examples are, you can also combine failure of processes with failure of links. So you can have the crash stop for plus the link failures. So a link, we have done this. A link fails by losing some methods, but does not delay the propagation of methods, for example. Does not duplicate methods and does not corrupt methods, but may drop some methods. So in reality, there are all sorts of assumptions we can make about links and processes. Okay? So another one would be, for example, the receive omission failure, where a process fails by receiving only a subset of the method that was sent to it. So, back to the question, which model when? So in reality, models, they help understand how the attributes of a system, they affect its feasibility and the cost of solving a problem. So I hope I gave you an idea of that by showing some examples where I had a problem that wasn't solved, and by showing also the example where you can have different cost of the algorithm in the case of the induction. Right? So how to choose? So that's I think the hardest question is how to choose a model for a particular real environment. So it depends on many things, on the kind of problem you're trying to solve, for example. What I mean by that is if you're trying to implement some protocol that's going to be used in a database, for example. So database by definition they can fail, they can recover. So it's kind of weird to assume that processes they crash and they never recover if what this process is going to do is to run a database. And then what are the risks of a failure scenario, for example? In some contexts where security is important, which basically means that there are outside processes that can behave in any unexpected way, maybe the best thing to do is to assume that these processes are Byzantine, meaning that they can do whatever possible to break your protocol. And as a consequence, your protocols are going to be more expensive. So here's a final example in this topic, and this one that we're going to use in the following lectures is an example taken from communication. So one kind of assumption we're going to make sometimes is that channels are reliable, and here's a more or less precise definition of what I mean by reliable. So if a process P sends a message M to a process Q, and Q does not crash, does not stop its computation, then Q receives message M. Okay?
This is the definition of reliable channels.
Yes, it's a definition of reliable channels. So I'm saying this is what the system gives you, right, to build a protocol. I mean, it's part of the model, right? I'm modeling my real system using this definition here. So here's an alternative definition, which if you read very quickly, you may just sound the same. And I'm calling this quasi-reliable channels. So if P sends a message M to Q, and both P and Q do not crash, then Q receives M. So what's the difference? So in the second case, I'm saying that the message is only received if both do not crash. So which one do you think makes more sense in practice? Wait a minute.
I mean, it depends on the protocol used.
Depends on the protocol used.
For instance, if you use the TCP we've mentioned here, and if the application crashes, the RST packet is sent, and if it arrives faster than the packet you sent before, the queue will not receive the message. So
yeah, what happens if you send a message, the message gets enqueued somewhere, like I don't know, local process, and then the process crashes?
So if the process before the crash informs the queue about its crash, the crash and fall packet will arrive probably.
Right. If you manage to send a message through the queue before it crashes, but you don't know, right? It may actually crash during the time it's enqueuing something. So before you put the message on the wire, so it's hard to tell. So if you want to play safe, assume that your communication links are quite reliable. Because in the quasi-reliable case, it means that the message is only received if both sender and receiver are operational. So the sender has all the time to place the message in the buffer, receive the message from the buffer, send to a switch, and so on. Now, I think that assuming that channels are reliable is a little bit dangerous. Just to complete the difference between the two of them. So here are all possibilities, right? When two processes communicate. So P sends a message to Q. So you have on the top left the message is received, there's no crash. So on the right, P sends a message to Q, the message never gets to Q. And here P fails and the message is received by Q. And then on the side, P fails and the message is never received by Q. So some of these executions, they satisfy the definition that I showed before, and some do not, right? And it turns out that these are the cases. So in the blue area, this blue in my computer, it's all the executions that satisfy reliable channels, And it turns out that these two on the outside the box, they do not satisfy. So based on the execution that is a little bit problematic is that is the one in here, right? He sends a message, it crashes, and then the message doesn't write because, for example, it crashed while the message was still in the local buffer, and this is not accepted. So if the real system that I'm using, or what I'm going to run, the protocol that I designed in this model here, this happens, then it may violate my algorithm is not going to work properly, right? Because I designed my algorithm with the assumption in mind that if the receiver is up, the message is going to be received. So if you take reliable channels, so this is captured by this assumption as well. Okay. So the question I have for you is, quite reliable channels is a better match to real channels, or I hope you guys got convinced that reliable channels, they make too many assumptions about how the systems work in reality. Do you agree with that? Kind of. So the question is, so why bother about reliable channels? Or even try to model a system as a reliable channel? Well, there are maybe cynical answers to this question, right?
There are systems which behave like reliable channels.
Yeah, you could find some system that would behave like a reliable channel in general, but it's a very strong assumption on how devices communicate. It basically means that if the sender fails at any point, but manages to send the message has to be received, right? So it's a very strong assumption. I don't know whether you could build a device that behaves like that. Well, it's simpler to solve a problem if you assume that the channels are reliable. Simpler than if the channels are twice reliable. That's for sure. So another reason is if you model your system as a reliable channel, right? So if it acts as a reliable channel, it's going to be quite reliable as well. Is that if you want to prove some lower bound, right? And you can show lower bound means some impossibility result. So if you can show that something is impossible using reliable channels, you know for sure that it's also impossible using quasi-reliable channels. And then we can work your proof there easier, more easily. Okay? So that's the first part. I don't know if you guys have any questions. If not, I suggest that we go for a 5-minute break, and then I will start with the second part of the lecture. What time do you actually start? Okay, so thanks for coming back. We're going to tell you about the consensus problem. It's probably the most discussed problem in statistical computing. There's a lot to be said about this problem. One of the reasons is because it's a truly fundamental problem. As I briefly commented before, many problems in reality, although people don't say that, but what they are doing is they are solving consensus. Right? In one way or the other, what they are in reality doing is solving consensus. Sometimes it takes a different name. Sometimes you refer to this problem as some existing algorithms. And in reality, let me ask a question here. How many of you have heard of the Paxos protocol? Okay, I'm going to tell you something new. So it turns out that Paxos is the protocol used at the core of Google, for example, and in several other systems. And in Paxos, what it is one way to solve the consensus problem. Now, we may think, well, this problem must be really complicated, because in reality, it was defined several years ago. It started in a particular context, and in the late 70s, and it's like more than 30 years, right? And people are still writing papers about the consensus problem. So you may think, well, this must be like, it's going to take me, I don't know, a few dozen of slides to define the problem. But it turns out the definition is quite simple. And here's the thing, right? Maybe one reason why people have studied this problem so much is because it's very easy to define it. It's not easy to solve it. Okay. So the problem, this is an informal definition, right? I'm going to be a little bit more formal later. So each processor has several processes. Let me tell you a little bit about the model. So the model has several processes. These are the units of computation. And these processes, they are connected to other processes But all each process is connected to all other process through some communication link. So they don't share any information. They don't have shared memory. They only talk through links, right? And each one is supposed to output the same value. So they start with some value, which doesn't really mirror what the value is. They start with some value. If you want to make things very simple, it's a binary value, 0 or 1, right? So they can communicate by exchanging messages, and at the end they should agree on the output. But the process is such that the output should be related to the input in the following way. So if you take this binary consensus, for example, 0 or 1, if everybody has 0, so the output should be 0. If everybody has 1, the output should be 1. If some have zeros, others have 1s, doesn't matter. It can be 0 or 1. Can make it quite simple. Okay? So that's basically the informal definition of consensus. And let me illustrate this, although I guess it's all right. In the rest of this talk, I'm going to represent processes by the circles, right? And then I'm going to represent the network by these wires, okay? Strings. So it means basically that each process can talk to each other process in the system. So here they have different values represented by different colors. They are going to exchange some messages according to some particular protocol. And eventually they are all going to reach a final state where they agree on a particular color. Okay? So that's what the problem is about. That's simple as that. So a little bit more about the failure model. I'm going to assume crash stop. So as I said before, processes they can perform for some time, and in this process they may fail, right? And when they fail, they stop the computation. They don't do anything else. And I'm going to call processes that never crash correct. These are correct processes. And processes that are not correct, they are faulty. Okay, so there are only two kinds of processes. Correct, they execute forever. They perform steps forever. They can send messages. They can receive messages. And faulty processes, at some point, they fail. Okay, they stop their execution. So let me give you so that's basically it. Right? I'm not saying that all processes crash, but some processes may crash. And I may also specify how many processes can crash, actually. Okay, I'm going to do that later. So here's the formal, a more formal definition. So the problem is defined by two primitives. One is propose, where I have a B as a value, and the other one is decide. So process they start by executing a propose. Each process executes a propose with some value. They are going to do some computation. Right now it doesn't matter how they do this computation because I'm talking about the problem. And define the problem. I'm not talking about a particular algorithm. So they do a propose with some value, they execute some computation, and eventually they decide on some value. And it turns out that this propose and decide, they satisfy the following properties. So the way I'm presenting the problem is by listing all the properties that are satisfied by propose and decide. So there are four properties. First one is agreement. So he said there's no two correct processes. So remember the notion of correct and faulty. So no two correct processes, they decide on different values. Okay? So termination. All correct processes, they should eventually decide. Right? I cannot impose such a thing on faulty processes because maybe they fail before the computation. So it would be a trivially impossible problem to solve if I try to impose termination on all processes. So I don't require all processes to terminate. But the correct process, they should terminate. Finish and decide on some value. Then a validity property, actually let's start looking at the first three properties only. The validity property says that if all processes start with the same initial value V, then V is the only possible decision value. Okay, so that was the property that I stated when talking about the binary consensus. So if they all start with 0, so 0 should be the decision. If they all start with 1, so 1 should be the decision. If they start with zeros and ones, I don't care. Okay. So this is one way of defining the problem. So a stronger way of defining the problem is that any decision value is the initial value of some process. Okay. I'm saying this is stronger because if I have this property here, I'm going to have validity as well, right? Because if they all start with 0, so by strong validity, any decision value is the initial value of some process. If they all start with 0, the decision has to be 0. If they all start with 1, the decision has to be 1. In the case of binary consensus, there's no big difference between these two properties. But I can use consensus to reach agreement when the values is anything. So I can assume that my values are integers, for example. And I'm not limiting the range of these integers. So each process proposes one integer. You should all decide on the same integer. And then according to one of these validity properties. Okay? So the definition is basically agreement termination in one kind of validity. Either validity or strong validity. Is the problem clear? Okay. So it turns out that I can change this definition as well, and I can revisit some of these properties. Like I can make them uniform. So the uniformity is a property that applies. It's a characteristic that applies to some properties, but not all of them. But I can have a uniform agreement, for example. The difference is a little subtle with respect to no uniform agreement. Here what I say is that no two processes they decide on different values. Okay. So before I had no two correct processes decide on different values. So you can have a stronger version of consensus. So in the previous version, I can have a process that decides on some value and crashes, and the others are going to decide on something else. Right? Maybe in some contexts that property is fine. In some other contexts, maybe I want something stronger, which basically says that no two processes decide on something else. Okay? But this property cannot be applied to this uniformity cannot be applied to all properties. So, as I just told you, I cannot change termination to have uniform termination because that wouldn't make sense. It will make a problem that's trivially impossible to solve. Because if a property says that all processes, despite their being correct or not, they must decide, it suffices for one process to crash and my problem can be solved. And I can't have it beforehand. So that would be a trivially impossible to solve problem, right? So I'm not going to change termination. I'm going to say that all correct processes eventually decide. I'm not saying anything about crash process. And then my strong validity is that any decision value is the initial value of some process. Okay, so I change that one here. So the point here is just show that sometimes I can have variations that are not really obvious at first, right? And this happened for the agreement property when I change from agreement to uniform agreement. Okay. So let's have a look at this consensus problem. First in synchronous systems, okay? And so to remind you, so the synchronous system means that I have some bound on the time it takes for the process to execute, and I have some bound on the time it takes for methods to be propagated. So the execution begins with all processes in some arbitrary start state, and the communication channels are all active, okay? And then in lockstep mode means that they are going to proceed in the same way in several rounds. The process they do the following. So first they apply some message generation function to the current state of the process. Okay? And this function is going to generate the message that the process is going to send. And then they send the message through all outgoing neighbors. Okay? And then, so this process is going to, some messages are going to be received. So what happens is it applies state transition function to the current state, the local current state, plus the message that has been received. Okay, so I think I have a picture here which simplifies. So I'm going to call this a round. So they all execute a sequence of rounds. In each round, what they do is they apply some function to generate the message they're going to send. So they send these messages. They receive the message that were sent during the round, at the end of the round, and then they apply the function to create a new state. Right? So that's nothing extraordinary. Now, what happens if a process crashes? So if a process crashes in the middle of the message sending, so only a subset of the messages may be delivered. Okay? Because that's the assumption I'm making when a process sends several messages. It crashes, maybe some messages are not sent. Okay? And I assume that at most F processes can crash. So I'm establishing a bound on the maximum number of crashes that my algorithm tolerates. So I'm going to design an algorithm, and I'll show you an algorithm that can tolerate up to F failures. Okay. So here is basically an illustration of how this algorithm works. So we have a sequence of rounds, right? I have 3 processes here. And in this particular case, I'm assuming that in each round, a process sends a message to all other processes. So P1 in round 0 sent a message to processes P2 and P3, and P2 did the same, and P3 as well. And note that there are some there's a bound in the time it takes for a message to be sent from one process to the other. And all these processes, they stay here, they receive so they all terminate at about the same time. They apply the function, they send some message depending on this function to the other processes, they receive the message and they go to the next round. And now here, in this particular round, notice that there was a failure of process P1, right? So what happened as a result is that P1 managed to send some of the messages that it's supposed to send in the round, but not all of them. So in this particular case, P1 sent a message to P2, but the message that P1 sends to P3 wasn't received. Okay? Because that's how in modeling fails. So here's the algorithm. And by the way, it guarantees uniform agreement and termination and validity. Okay? So uniform agreement, if one process decides a value, so no two processes decide different values, despite them being correct or not. Okay? Uniform agreement. So it guarantees termination. All correct processes, they are going to decide some value. And it guarantees validity. So the value that's decided. So if they all start at the same value, that's the value that's going to be decided. Okay? So the algorithm works like this. So each process maintains a variable W containing a subset of V. Okay? And initially, process PI's variable W has only PI's initial value. So its own value. So V is the total set of the set of possible values that process can have. Okay, first they may or may not know this. So initially they have in this variable W only their own proposal. Okay, so each process knows its own proposal, right? It's what's executed by the proposal, small v. And that's the only thing it has in W. Then what it does is it executes F plus 1 rounds. Okay. And in each round, the process broadcasts the set W, which contains all the values it has seen so far. And then adds the elements of the received set to its own local W. Okay? So basically what this algorithm what we're saying here is that a process gets the set of all values it has seen so far. In the very beginning of the execution, it has only its own value. Then it sends this value to all the other processes. So at the end of one round, each process collects all the methods that were sent, and then groups all the values received in the set value. Okay, and then sends them again in the next round.
And by the way, we assume that all processes have a link.
Yes. Okay. Yes. Thanks. So each process has a communication link to every other process. Okay. So that's why in the beginning I had the picture. I have a fully connected graph. You can also study this problem in partially connected graphs. But it turns out that things get considerably more complicated if you have partially connected graphs. So the question is why? So why if you have a partially connected graph, you instead of having one process connected to every other. So here I'm assuming the implication of having a fully connected graph is that between each pair of processes there is a communication link. Okay. So I could assume something more general than that by saying, I can have any subset of a fully connected graph. Usually that assumption is not there are some studies that consider that. The problem with such an assumption is that sometimes the failure of a process prevents correct processes from communicating, because maybe the only way for two processes to communicate is going through the two processes. So it makes things a little bit more complicated. So let's assume here, to keep things simple, that there is a connection between any two pair of processes. So that's what they do, and after F plus 1 rounds, so remember that F is the number of failures that my algorithm can tolerate. This is a parameter of the algorithm. So after F plus 1 rounds, PI, every process PI, decides on the unique element of W, otherwise PI decides on the default value is 0. Okay? So this is validity, right? If they all start with the same value, they have to decide on this value. If they start with different values, it doesn't really matter. They can decide on anything. So this algorithm decides on this 0. For those who don't remember, let me go back here to the project number. You won't appreciate the algorithm. So if our processes start with the same initial value V, then V is the only possible decision value. If they start with different initial values, it doesn't matter, right? And we can decide on some default value. It doesn't matter the decision. So that's why in this algorithm here, after f plus 1 rounds, we decide on the unique element of W. If there is a unique element in W, it means that they all propose the same. Right? Now, if there is more than one element in W, it means that at least two processes, they propose something different. And then, by definition of validity, it doesn't matter what the value decide. So they're going to decide on default value. Easier. Okay?
And once again, how does PI decide after f plus 1 rounds?
So by decide here, what I mean is, it is executing the primitive decide that characterizes the end of the computation. Right? It's a proposed decide. Once they execute decide, it means that it's finished. So it decides on the unique element. It means that it executes this decide element, meaning that it has reached it has terminated. Now, in decide on which value? Well, it's what this thing here says. It's a unique value in W, if there is a single value in the set W, or on some default value if there is more than one element in W. So here, decide means it executes the primitive decide characterizing the end of the computation.
Why do we need f plus 1 rounds?
That's a good question. So why do we need f plus 1 rounds? Maybe you could decide before f plus 1 rounds. Well, let me answer this question by showing very quickly, really, just a bunch of lemmas that characterize the correctness of this algorithm. So basically, going through this, I hope you get the intuition why we have to do f plus 1. I can tell you something more. So these are a few properties of this algorithm. Okay? The first one says that if no process fails during a particular round, right? If there's a round that all processes execute from beginning to end, right? They all send their methods, and they receive all the methods. Then it turns out that if you take the set of any two processes that execute this round, this set is going to be the same. Okay? We move back here. So if they all execute a particular round, it doesn't matter which round it is, but if they manage to execute all the same round and no process fails, at the end of this round, they are all going to have the same set W. Is it clear why? Because, well, they start with some W. Maybe they are different here. But they send this W to all other processes. And each process does the same, right? And since I'm saying that the round here, if no process has failed in this round, at the end, they do the union between all the W's they received, they're going to finish the round with the same set. Does this sound plausible? Okay? So it suffices to have one round where they all execute to have the same value for W. Okay?
And then once again, what is the crash?
What's the correction?
The crash. What is the crash?
Oh, the crash was defined here. So if a process crashes in the middle of so it's crash stop. I had before. So it's if a process crashes, it stops computing, and then a subset of the methods may be used.
And doesn't do anything then, yes?
No, it doesn't do anything then. Yes, it crashes and it stops.
So it never sends something wrong, yes?
No, it never sends anything wrong. No, by default, I'm not considering Byzantine processes. What they send is correct. Yeah, if they send something wrong, it's a different story. So no Byzantine failures of any sort. And a crashes, they stop their computation. And as a result, only a subset of the methods may be deleted by the other processes. I'm not saying what the subset is. Maybe all the methods are received. Maybe no message is received. But maybe a subset is going to be received only. So the second property is, so assume that two processes, they have the same W set. Okay? For processes PI and PJ, they all have the same. And they are active after R rounds. They have executed R rounds and they have all the same set. Then for any round R prime, that is bigger than R, smaller than F plus 1, the same holds. They're going to have the same value for Wi and Wj. For all processes that are active after R prime rounds. So is that Do you believe this?
Can we come back to algorithm, please?
Okay.
What do you mean by adds all the elements? It adds to.
It does the union between all the W's that were received. Adds all the all the elements.
It gets a set of values, yes?
Yes.
And then after each other step, it sends a set of values, yes?
So what it does is, it has, in the beginning it has its own set, right? Sends the set to all the others, and receives the set from all the others, or maybe it was from a subset of them, because if one fails, it receives from a subset. And then performs the union between everything that was received. So basically it's,
Okay, and then what is the choice in the very end? In the
choice.
very end, it should choose the value, yes?
So this.
So how does it choose? I don't understand.
It basically it executes f plus 1 rounds, and then it looks at the resulting data that was computed based on these steps. Right?
This is a big step, yes?
Yes. Each process has only a single set, right? And it keeps adding things to the set, right? Basically, the way it does it, once again, it sends its own set to all the others. Everybody does this. By the end of the round, you have received the sets from different processes. You compute the union between all the sets. And this is your new set.
Okay, and how does it decide on the W?
So, basically like this. Decides on a unique value of W. If it looks at the set W, there is a single value. Right?
It has some decision function.
Yeah, well, it doesn't matter. Yeah, there's some decision function that does basically this. But this is the decision function. It looks at the W set, the subset W, and then it decides on the particular element if there's a single one. It's a deterministic function for everyone. So the only source of non-determinism here is W. If they have different values, they need reach different results. But if they all have the same value values, they're going to decide on the same thing. Okay?
Could you please where does the default value D0 comes from?
It's a hardwired in the algorithm. It's some value D0. It doesn't matter. Right? But it's hardwired in the algorithm. They all are going to do the same. Well, it doesn't really matter. Don't care. It could even be different value. If you look at the validity property, the only thing it says is that if they all start with the same value, it has to be the same. If one process has a different value, you can decide anything. Okay? But it has to be the same. So because agreement is still there, so they have to decide the same. Okay, but it has to be it's a value that's hardwired. So all processes are going to decide the same thing. Okay?
One more question, please. What does it mean, otherwise, mean in that context, in a last sentence?
Yeah.
It seems that after f plus 1 rounds, we already have set W on each process, so we can define value for sure. So what's the meaning of otherwise? And
so it means that what can happen here is otherwise, because maybe there is more than one element in set W. They all have the same, and that means there is more than one element. Because the size of W, it depends on the proposals.
So you mean if set WY has only one, only unique element, we choose that element. And
otherwise, if there's more than one element, then we decide on this zero.
Now it's clear.
Okay, and then the final one is, so this is a conclusion from the previous, if process Pi and Pj are active after f plus 1 rounds, then they are going to have the same set at the end of the round, and then basically they're going to reach the same decision. I think the thing, maybe it is not clear by now, the observation to realize why this thing works, right, is why f plus 1? Because in reality, you have to make sure that there's going to be at least one round in this execution where all processes are correct. So there's no crash. There's one round where there is no crash to the code. Because from level 1, which is basically the core of the correctness of this algorithm, is that if you have one round where there is no crash, they all agree on the value. Right? So how do you ensure that? by requiring f plus 1 rounds, and f is the number of failures. So if only f processes can fail, right, there's going to be at least one round, maybe the last one, where they all execute. If they all execute the round with no crashes, they exchange their sets, and then they have the final, the similar. That's basically the correct assumption.
I'm sorry, and can faulty process just keep running after the f plus 1 rounds and crash sometime afterwards?
If a process can, yes, it can. So what it means is that for the purpose of this algorithm, this process is correct. In fact, that raises another issue, which is, I briefly said, but it didn't go into too much in detail, that corrected processes are processes that never fail. So if you take this, so strictly speaking, during the whole execution, which means forever, the process never crashes. Well, it's a little strong assumption, right? Because it means that you have to build a computer that will never fail. Once it starts, it will never fail. It's hard to believe that can be done. But it makes simpler to define correct process, right? It never fails. Now, in reality, what does correct really mean? It means that from the beginning of your computation until the end, the process is going to be there, doing something. Maybe after you decide, then I don't care about this process anymore. At least not in this algorithm. Okay.
Once again, about crashes. If a process crashes during round R, the next round it still can...
No, that it can't. Right? If the process crashes round R, then it's not going to execute R plus 1. That is a good point. Maybe this algorithm would even work in that case. We have to think more about that.
But it seems it doesn't matter for correctness. Am I right?
If it continues computing after...
Anyway, it can come this communication protocol by doing something after crash.
Say it again.
I mean, if crash process still working after crash, it can't harm anyway our communication protocol. I mean, correctness still exists, remains, and so on.
Yeah, I'm not sure about that because it really depends.
How it can harm? After f plus 1 steps, all processes have the same set W.
So after f plus 1, it doesn't matter. The problem is finished. But I think what I said is, what happens if a process crashes, I don't know, before this f plus 1, right? Execution, f plus 1 takes this, the process crashes here, and then continues executing before the f plus 1. If it's after the f plus 1, yes, I don't care. They all decide. But what happens if from the beginning, between the beginning and the end, a process crashes and continues there?
In that case, it does matter because if it crashes, for example, initially at 0 step, and then we'll rely, I don't know what to say, after f plus 2 steps, no one will know its own ID.
No, but don't say that. Okay, I see what you mean. But it's a synchronous system, right? Or you assume that they always start at the same time. So they are executing these steps, all these rounds in lockstep. So they start the first round, and they jump to the second and the third. So there is no, I see what you mean. Like one starts a little later than the other. So for this one starting later, f plus 1 means f plus 2 to the others, right? So that cannot happen here.
In our problem, we wanted all processes to come to consensus, yes?
Yes.
And crashing processes needed to come to consensus too, yes? But
No.
they don't.
No. That would be impossible to ensure. Let me go back. You don't even have to look at the algorithm. Just look at the properties is enough. Look at the definition here. So termination. We're talking about termination, right? Which basically is a liveness property. All correct processes must eventually decide. I'm not saying anything about faulty processes.
So does this algorithm ensure uniform consensus or just consensus defined on the previous slide?
That's a good point.
We have our V0 and we can't be sure that V0 was the initial value of some process.
Oh, it's not strong validity. That's a little bit misleading. I'm using this definition here to talk about termination. But if you look at the algorithm, it's uniform agreement, termination, and validity. Right? It's not strong validity. So it means, validity means, once again, if they all start with the same value, they should decide on this value.
Okay.
And nothing else. So the zero is fine if they don't start on the same. Now what we are saying is, so somebody else talked about agreement, so it's uniform agreement, right? So I'm saying that if a process decides, it has to be the value that other processes decided. That's what uniform agreement says. But termination says that if the process is correct, it's going to decide something. If the process is faulty, I can't impose this, right? It would be a meaningless problem if I have to try to impose termination on processes that are not correct.
So basically, strong validity is not a property of uniform agreement.
No, these are different properties.
Okay. It's just shown on the same slide, so.
Oh, what do you mean?
A bit confusing. If you go back to the definition of uniform validity.
Well, I think you can fix that.
Strong validity is
I'm going to have to use your laptop.
So basically, you can see the definition of uniform consensus. It seems like it has a strong validity property, and we can show strong validity now.
Sorry about that. I shouldn't be referring. Well, that's the only slide I have with all the it's the closest slide to the algorithm with all the definition, all the properties. But if I go to the algorithm, back to the algorithm. So what I mean by the things between parentheses there is that it's uniform agreement, termination, and validity. Okay, so before I get to that. So I hope you guys agree with me, or don't have some time to think about this. Now, what do you think about the asynchronous model? How much more complicated do you think this algorithm is going to be when you take the asynchronous model? Look at that. It's not very complicated, but it's not straightforward either. The consensus algorithm for the synchronous model. And as I said in the beginning, the synchronous model is much stronger than the asynchronous model, which makes algorithms simpler. Right? Now, what do you think about the asynchronous model? How much more complicated do you think the algorithm is going to be in the asynchronous model?
And sorry, can you specify the problem for asynchronous model? Because if we don't know anything about delays,
sure.
In 1 year, how the messages...
Yeah, I can specify the problem. So here's the problem. It's the same problem. Doesn't change anything, because as you can see in the definition, there's nothing about...
we don't know anything about delays yet.
You don't know anything about delays, so that's about the model. Right? The asynchronous model doesn't make any assumption about delays. So you don't know how long it takes for a process to execute a step. You don't know how long it takes for a message to be sent.
Okay, so what the word eventually means?
Eventually means that at some time in the future, this thing is going to happen. It's going to happen, but I don't know when. There's no notion of time embedded in the definition. So if there was a notion of time embedded in the definition, I could tell you immediately, it's impossible to solve this. So let's remove any synchronous, any mention of time from the definition. Right? There's nothing about time. Besides the fact that it says at some point in the future, which I don't know when, the process is going to decide. So because I still have some time, but I don't have much power. Let me give you the answer. So it turns out that, and this is one of the most fundamental results in distributed computing, that it's impossible to solve the problem. So there is no algorithm that can solve the consensus problem in an asynchronous system. Right? And this is a result that has been known for quite some years. So you may be wondering, so I said at the beginning, for the past 30 years, people have been working on the consensus problem. It is as simple as, the synchronous algorithm is not that complicated, and there is no asynchronous algorithm, so what the heck have you guys did for 30 years, right? There's a lot of things we can do to actually get around this impossibility level. Okay, this is just recalling the model. Our process begins in arbitrary start states, and now channels are empty. Then processes do what they can do in a asynchronous model is apply the message generation function to the current state of the to generate new methods, right? They apply the function to the current state, generate the message they want to send, they send the messages, and then what they can do is they can wait for a certain number of methods, right? But differently from the synchronous system, where they wait for the end of the round, and end of the round here means something. It means really some time, right? Because there are strict bounds on the time it takes for messages to be propagated, for processes to execute. The process can wait for some time, and it knows that that's the end of the round. So the methods that were sent in that round, they are received at the end of the round. But here it's different. It's an asynchronous system. So you don't know how long it's going to take for a message to be delivered. So the process, they cannot wait until the end of the round, because maybe this end never comes. There's no sense in waiting for the end of the round, because you cannot measure time. So the best they can do is, they can wait for n minus f methods, where f is the number of processes that are full. Right? Because they know that for sure they're going to receive n minus f messages. Why? Well, because these are the processes that are correct. Maybe if it wait a little bit longer, it would receive one more message. But maybe this message will never be received. And it doesn't, there is no sense in waiting a little bit longer, because you can always delay the messages so that they arrive after the process gives up on the message. Okay? So what they do is they can wait for n minus f. And that's how they're going to define a round here. So, just to recall everything, synchronous versus asynchronous. So synchronous looks like this, everything will be fine, and asynchronous looks a little bit more messy. And the reason is because I can stretch these lines here as much as I want, right? Because that's what it means for a system to be asynchronous, and that's what it means for a message to be received at any point in time. I can simply stretch these things. But what you can see from this picture is that the processes, there is still a dashed line showing the beginning of one round and the end of the round. But the difference now is that what defines the beginning and the end is the number of methods that a process receives. Because that's the best it can do. I cannot do anything more than that. It turns out that in this complicated picture, it's impossible to solve consensus. Right? There is no algorithm that can. And it's even the result is even more surprising, because it holds even if a single process can fail, despite the number of processes that have performed the computation. So imagine that you have 100 processes, they want to reach consensus, they run in an asynchronous system, and one can fail. So it turns out that there is no way to finish them. You cannot reach consensus. Now, we have to be careful about when interpreting this result, right? What it means that no algorithm can solve this problem. It means that if you write a smart algorithm, and you should try very hard, this algorithm is going to work in many cases, right? But there's always going to be one case where it's going to fail, and that's basically what this result shows, right? So if you are looking for an algorithm that solves the problem in every execution, so you should give up. There's no way to solve it. So, how people have spent, including myself, their times in a problem that cannot be solved in asynchronous systems? Well, it turns out that there are a few things we can do, actually. So one of them is that we can weaken the problem a little bit. So maybe consensus as presented so far is too hard a problem. And then we should work on versions that are a little bit weaker than that. And maybe by defining a version that's a little bit weaker, you can actually solve the problem. So another thing you could do is strengthen the model a little bit. Add some other assumptions about the model. In one extreme case is that add so many assumptions that we're going to end up in a synchronous system. So you don't want to do that. But you don't have to do that. You don't have to add so many assumptions so that your asynchronous system becomes synchronous. There are things in between, as I said, the asynchronous and the synchronous, that allow you to solve the problem, and some realistic enough that could